Before we begin today, you are about to listen to episode 100 of the Gradient Podcast. This seems like a good time to reintroduce what we're doing here for those of you who might have joined us more recently. As I mentioned pretty much every episode, the Gradient is a volunteer-run project by a few engineers and grad students. This show is a one-person effort where I hope to bring you some of the most interesting voices thinking about AI right now. That includes people from both inside and outside the field. And in that vein, if you've listened to the show for a while, then I'll hope you've picked up that it's not a show entirely about trends, but one more about stories and people and ideas. It's about the different ways we can think on a capacious field full of difficult to define concepts and hard problems of many different types. If you like what I'm doing here, and I do hope to continue doing this, your support does mean a lot. I appreciate reviews, and it's great to hear from you if you have feedback, guest suggestions, comments, or anything else to send my way. You can reach me via editor@thegradient.pub, and you can always leave us comments on Substack. I do read all of your comments and find them very helpful as I continue working on improving the show. Your reviews as well help people find us. They help me figure out what you like about the show as I keep doing it, and it makes a kid in his mid-20s very happy indeed. And finally, as I mentioned, this is a volunteer project. Our funds currently go towards site upkeep and ad hoc expenses, but if you do want to help create a world in which we might have enough funds to compensate our editorial staff, then you can support us with a paid subscription through Substack or through Patreon. Once again, thank you so much for listening and for your support, and I hope you enjoy the episode. There are far too many challenges in machine learning to describe in any reasonable amount of time, from fundamental questions about how we think about knowledge and understanding in computational systems, to difficulties in applying ML techniques to areas like ecosystem informatics. Professor Prof Dietterich is a brilliant and prolific researcher whose work has tackled many different types of questions AI researchers find themselves trying to answer. And he has thought incredibly deeply about the even more basic problems facing the field. From his early work describing knowledge-level learning, to his more recent ideas for developing high-reliability AI and for developing modular intelligent systems that can do things language models can't, Professor Dietterich has carefully considered what the important problems and goals for AI research are. This was an expansive conversation covering a great deal of Professor Dieterich's career. I hope you'll gain some perspective on not only how ML has changed over time, but also how Professor Dietterich thinks about scientific paradigms and what the field ought to be thinking about next. This is the Gradient Podcast, and I am your host, Daniel Bashir. If you enjoy these episodes, you can follow us wherever you're listening to this podcast episode. You can also follow us on Substack to get regular notifications whenever we release a new article, newsletter, or podcast episode. You can also find our online magazine at thegradient.pub, where we regularly publish essays by the sorts of people I interview on the podcast. And finally, if you enjoy the episode, it would mean a great deal to us all if you'd consider leaving us a review on whatever podcast player you're using to listen to this episode. It helps more listeners like you find what we're doing, and helps us bring in more interesting guests for you to listen to. But now, without further ado, Prof Dietterich. Professor Dietterich, you're often called a founder of the field of machine learning, which I don't know how you feel about the label, but it's hard to dispute that you've made a number of very important contributions to both basic research in the field and applications. And so my first question, as usual, is how did you get into AI in the first place?
So I did my undergraduate degree in computer science, not in computer science, in mathematics at Oberlin College, because there was no computer science really wasn't available at the undergraduate level back in the mid 70s when I was an undergraduate. But I had always been engaged with computers for a long time. My uncle was an early programmer on the GE time-sharing system at Dartmouth as an employee of General Electric. And so in my early teens, I had a chance to program in BASIC on that time-sharing system. So I mostly managed to skip the punch card generation and go straight to paper tape. But so I decided to apply to graduate school, not really knowing what graduate school was or what computer science was. But as an undergraduate, I had gotten interested in the philosophy of science a bit through a course on philosophy of political science, which is a back-end route. But I'd read Thomas Kuhn's Structure of Scientific Revolutions, and I was really intrigued by these questions of how is it that humankind has been able to learn over time, presumably more and more accurate models and theories of the physical world, the biological world, and so on. How does that process of conceptual change and knowledge growth happen? As one of the philosophers of science that I was reading at the time said, and how does it happen as a series of rational steps? Or is it more random? So when I applied to graduate school, I was admitted to the University of Illinois and contacted by a faculty member there, Richard Michalski, who was working in what came to be called machine learning. So Arthur Samuel, of course, in the late 1950s, had coined the term machine learning. I think that's the earliest mention we know of it. But it wasn't really used much in the 60s, and it was really in the late 70s. So I was applying to graduate school in 1977, or started in fall of 77. But Michalski was interested in trying to learn logical expressions that described situations from data. And in those days, we were very much under the influence of expert systems technology and hand-authored rules. And so there was the goal was really to learn correct rules from data. A little side diversion there is we often were not learning the correct rules, at least not the rule that we intended to learn these were mostly on toy problems. But what was interesting was the rules were almost always very accurate, even though they weren't 100% correct. And that later, following up on that idea is really what Leslie Valiant did in introducing the probably approximately correct framework for machine learning, which really said it's a statistical undertaking, not a sort of program synthesis. I think we were thinking about much more in the way of synthesizing code or synthesizing knowledge representations, logical expressions. There was a notion of correctness, and he was saying, well, the notion of correctness needs to be relaxed in two ways. It needs to be allowed to be only approximately correct, and you also need to be permitted to fail completely with some probability. And if you could take those two relaxations, then you could prove theorems about things that could be learned in polynomial time and space. But coming back to the story, so I was offered a research assistantship with Richard, and I took him up on it. And then I worked on problems. He was looking at his application work was diseases in soybean plants. After all, we're at an ag school at the University of Illinois, and so that was interesting work trying to figure out how to do that. My master's thesis was actually about a game that had been published in Martin Gardner's mathematical column in Scientific American called Eleusis, in which it's a two-player game. One player is the dealer, and the dealer invents a rule that will describe a sequence of cards that are legal to play, and then the goal of the players is to try to not exactly to infer the rule, but to play according to the rule successfully. So so you could play a card, and the dealer would tell you, yes, that's correct, that's a legal extension of this sequence, or no, that's incorrect, and so you get a negative training example. And so I coded up a very ad hoc program that, well, we played a bunch of these games among the graduate students, and then based on that sort of data set, I engineered a program that could play the game fairly well. For, I mean, the trouble is there's sort of an infinite space of possibilities, and so there are many things that I couldn't handle. But and so I had a little correspondence with Martin Gardner after that, which was fun. So in 1980, I had moved to Stanford University for the PhD, and but Richard Michalski, in collaboration with Tom Mitchell and Jaime Carbonell, who were I mean, I think they were both at CMU, or Tom may still have been at Rutgers. But the three of them organized the first workshop on machine learning, and Richard introduced that name and said, "Let's call it machine learning." I think that was a somewhat controversial because it was there's always been a tension about, is machine learning part of artificial intelligence or is it something else? And I think this was more of a branding exercise. But in any case, we had that first workshop, and there were about 30 people there. Herbert Simon gave the sort of keynote speech to these 30 assembled people in a classroom at Carnegie Mellon. But the about, why should machines learn, and a young guy named Ross Quinlan gave a talk on using decision tree algorithms. He proposed a new decision tree algorithm called ID3, and he was using it to take reverse enumerations of chess endgames and turn them into decision trees or rules that a person could use to play perfect chess in certain endgames, like king and rook versus king and knight kinds of these. So once you got yourself into an endgame, Ken Thompson, who was one of the co-inventors of Unix at Bell Labs, was also interested in chess and had been doing reverse enumerations from all winning positions in chess backwards, and building these huge tables with the idea that they could be somehow put into a chess playing program to play perfect chess. But Ross was interested in, could we boil it down to a set of rules that a human could memorize to play perfect chess? So that still shows that machine learning in that very first workshop was not statistical. It was supposed to be lossless boiling down of data into rules, sort of lossless compression in a human understandable way. And so I would say even toward the end of my dissertation work, that was still kind of the mindset of the community. And there were people involved in that community that were coming from, psychological models, John Anderson's ACT-R cognitive architectures, and so I'm trying to think. I mean, Doug Lenat was involved, so lots of different, very, very diverse philosophers, psychologists, computer scientists. Things. So after that first workshop, then I think we had a second one in 1982 that was at Illinois, and there we must have had probably more like 80 participants, and a third one in 1983 maybe that Tom Mitchell hosted in Pennsylvania. And at that workshop, he invited Leslie to give his PAC Learning talk as one of the invited talks. And so I think that's kind of the time at which we started to make the shift to thinking about things statistically. So I don't know. I don't count myself as a founder, maybe one of the early participants, but the founders really would be, Mitchell, Michalski, and Carbonell.
One thing that really stuck out to me in your story was the encounter with Thomas Kuhn you mentioned. And I wanted to pull that out for a second, just because I think that right now there are a lot of interesting takes going around, or ideas questioning, well, just what kind of discipline is artificial intelligence, is machine learning? There is a lot of banding around the idea that it's, at least at the moment, primarily an engineering discipline. And I think that a number of people I've spoken to, though, still really look at it with more scientific rigor. And I suppose this can, of course, depend on precisely the types of questions or precisely the end goals you have in mind. But Kuhn kind of interested me, and the thing you said about him was very similar to, I think, something that Karl Popper says in his Conjectures and Refutations about just the growth of scientific knowledge being this procession of theories that cannot ever be proven true. You can gather more evidence for them, and then you can conclusively prove them false. And we sort of iterate on that process to get better and better and better theories. And that's sort of how you have all these encounters with epistemological questions, the Kantian, critique of pure reason kind of being in that critical context of, well, we have the Newtonian theory now, and it seems to be just true. So how can we actually know something like this? I'm curious if that encounter with Kuhn with some of these questions maybe continues to influence how you think about what you are doing as a discipline and maybe the way you approach questions.
Absolutely. So my PhD advisor was Bruce Buchanan at Stanford, who was part of Ed Feigenbaum's very large lab, the Knowledge Systems Lab. Bruce was trained as a philosopher of science, and he was an instrumentalist. So we were never allowed to use words like real, true, genuine in anything, and he really sensitized me to this point that we can't know that our theories are correct, but we can evaluate them from evidence and from and perhaps also from their usefulness as engineers, and so I think just as an example, I've been an advocate of I would say of the Daniel Dennett takes that kind of perspective with respect to notions of knowledge, intelligence, agency, action, goal. The idea is that we attribute these to a system because they give us predictive power or explanatory power for understanding how the system will behave. But they are not real in any sense, in the sense that you could open up the brain of someone and find this single neuron that encodes their goals or something like this. And I take that perspective with respect to things like understanding. So I wrote this piece that was sort of an editorial, I guess, or a blog post on what does it mean for a machine to understand. And I'm really advocating that kind of an instrumental view that if the system responds appropriately, my example is if I tell Siri to call my wife and it dials the right phone number, it's hard to convince me that it didn't understand. I think it understood my request. But people say, yeah, but did it really understand? Was it genuine understanding? And I think that that's the wrong question. I think understanding can vary on a lot of different dimensions. It's going to be, it might be very shallow understanding. So I'm pretty sure Siri doesn't understand what it really means to be someone's wife or husband, right? All of the consequences of that, or really understand what happens after it invokes the dial this number API. Does it have any understanding that there's then a conversation and that information might be exchanged, promises might be made, there will be outcomes of that call that might influence future action and so on. I don't think it has no understanding of that. So understanding can also be, I would say, pointwise versus systematic. So Siri may know who my wife is and not be able to call anybody else in my address book, right? So this becomes an extremely narrow capability, a very narrow understanding. But maybe it systematically understands how to call anyone whose number is in my address book. That would be better. And of course, it'd be even better if it had the capability to say, well, I don't know that number, but I can go try to look it up online or look through your emails at signatures or something to try to track it down. So that definitely reflects this idea that the search for genuine understanding or reality is I almost use the word really is a doomed undertaking. That what we can do, though, is hope to try to build systems that are, have deeper, more systematic, more reliable understanding of our intentions and our goals and what they should be doing to help us.
In what you said about levels of understanding and the fact that they exist along a continuum, it's kind of interesting just to be careful about demarcating when we're describing properties of a system, those which will scale in ways that these do along a continuum and which might be binary properties. There was this big set of Twitter discourse that went on after Ilya Sutskever's tweet about today's neural networks may be slightly conscious. And I recall somewhere around that time, you had a Twitter thread where you made a very similar point about levels of sentience being on a continuum, which I thought was a really useful way of thinking about that particular debate as well. And just kind of looking at some of these things so that we want to ascribe, whether it's talking about understanding or sentience or even grounding, for instance. I think people have brought the idea of a continuum existing in that domain, although I think Harnad might maybe slightly disagree with that being a good characterization of what goes on with grounding. It seems like there's just still not enough nuance. It's either this is sentient, this is not sentient. And so it seems like, though, empirically, there are kind of only a few things we can characterize, right? It's what you said about there being measurable, kind of concrete capabilities we can look at. With deep learning, you sort of pointed out in this essay we're talking about that the connectionist methods we use now have very difficult to interpret internal structures. And of course, there is still work going on trying to interpret those. We have mechanistic interpretability, for instance, but you suggest that we should focus on desired behavioral capabilities and then ask how internal mechanisms achieve those capabilities.
Yeah, I guess right where I think I link up with Harnad in the sense that he wants to say that a symbol or a behavior is grounded if it can be causally connected to, say, the object in the world. Or and I wouldn't. I would say that on a spectrum of depth of understanding, causal connection is superb and very, very strong, and you would be very confident that the system has a systematic and deep understanding if it can achieve that. But I don't think that's essential. So that's and I think when he gets into this discussion of kind of indirect grounding, that the connection becomes more tenuous because it's not necessarily fully causal. And we see, I'm more and more aware of the shortcomings of statistical learning when we enter this space because, Udea Pearl has shown very convincingly that you cannot draw causal conclusions without making causal assumptions. And statistical learning has not been willing to make causal assumptions until, there's a small subcommunity working on causal modeling and causal learning. But I think that Pearl's work establishes sharp limits on what we can achieve using only statistical learning without introducing a broader framework of causal reasoning. And I think that that's sobering. We're seeing that we can get statistical learning to do beautiful things in language understanding, speech recognition, translation, computer vision, segmentation, all of these things with very high performance. And yet we also see lots of failure modes of these systems. And some of them are, I think, due to not really establishing the underlying causal understanding of the world. And I think this has engineering implications, obviously, as well. When I've been lately trying to think about how could we get any kind of confidence that a system had correctly achieved a systematic understanding of something. When we look at traditional software, we can compare how we design and test that software. The design and coding is done by a human who's generally thinking very causally and systematically about the domain. Right? Each basic block in a piece of code is supposed to is systematically handle some region of the problem space, the input space, or whatever, until you reach some conditional, and then it has to branch and so on. And then we test that code by testing its behavior on individual test inputs. And if we can ensure that we've covered every basic block of the software with a test, we're confident that because inside the block they're systematic, that gives us some confidence the whole code is systematic and it's covering everything. But with machine learning or statistical learning, we train only on data points, and so then we turn around and test again only on data points. So we are only testing the point-wise understanding of the system and not its systematic understanding. And so I think this is a interesting challenge for the machine learning community. Can we find ways of testing for systematicity in the system behavior? And we can see that this attempt to turn around and use LLMs to generate software, which we can then test and check in more traditional ways, is an interesting response and a very promising direction.
I want to quickly rest a second on the idea of robustness or depth of or systematicity of understanding being backed by this causal understanding of the world. There's, of course, and you'll be very well aware of the well-known problem of induction, and someone might take that to be skeptical of even your and my ability to form causal understandings of the world. And of course, I think Karl Popper, who we referenced earlier, has his own sort of solution to this, but I'm curious about how you think about the idea of our ability to form causal understandings of the world, and then what that says about the possibility of research programs to get, AI systems, computer programs to also develop that.
Well, I think we can easily imagine having a space of causal hypotheses that we're considering, and we can then collect data, do experiments, or take observations that can help us reason about those. We can be Bayesian about those different hypotheses and which ones are better supported by the evidence. What Pearl's theory tells us how to do is exactly that, to say, well, how do I remove confounding so that I can actually estimate the causal effects under various conditions and so on? And how can I convert the causal inference problem into a statistical inference problem? But you have to start with a set of causal hypotheses. So there's no fundamental barrier to doing this from a machine learning or epistemological standpoint. It's just that it requires a different set of machine learning algorithms than the ones that have basically been based on fitting flexible data sponges or functions, which is what we have with deep learning or decision trees or generalized additive models or whatever your favorite family is.
Before we move on from this section, you have this other paper called Learning at the Knowledge Level. And what I was hoping we could kind of get out of this paper is maybe to build up the tools to make sense of this statement. You wrote that the approach in the AI community is seizing the search for a general theory of non-deductive knowledge level learning, and instead to focus on the development of induction methods that appear to give good results in practice. And I think parts of that sentence are going to ring familiar and make sense to people who are listening right now. But I think that there are terms here like non-deductive knowledge level learning that might be interesting to introduce. And so you introduce in this paper sort of ways to describe systems, what you call the knowledge level, and you introduce knowledge and symbol level learning. I'm wondering if we could maybe rehearse a couple of these definitions just as a framework for how you were thinking about systems at the time.
Okay, yeah, sure. My paper was building on top of Alan Newell's AAAI presidential address from I think 1982, where he talked about introduced this notion of the knowledge level, and that in turn was building on Daniel Dennett's notion of the intentional stance. So Newell was really asking, can we take Dennett and actually somehow make it real? So I think Newell argues that there are multiple levels of descriptions of systems, and that they can be viewed as behavioral laws for those systems. So he's very much, and I think many of us as engineers are very attracted to the idea that we can start with circuits and then build logic and adders and multipliers and CPUs, and then we can build operating systems, and then we can build compilers, and then we can build software, and then we can build distributed systems and networks, and the whole thing is reducible, right? So it's a reductionist dream that you can take a phenomenon at a very high level of behavior, even something like ChatGPT, and go all the way down to what gates and what depletion regions in semiconductors led to that output. And Newell wrote books on computer organization, among other things, in his amazing career. And so he was trying to argue that there is a kind of a level at the knowledge level that is similar to these other levels of description. He admits that it's not quite perfect, and I would say that it's still a level at which we ascribe behavior. We talk approximately about the idea that a system, if we're trying to predict the behavior of a system, and we can attribute goals to the system. So we can say the system has this goal, and then we can say, well, if the system also has some knowledge, then it will use that knowledge to achieve its goals. So if the system has, I don't know, the goal of purchasing a car, well, maybe that's too big. Maybe making an online purchase. So maybe it wants to purchase a mouse or something, and it has knowledge about a credit card. Then it could use that knowledge we would predict that it would use that credit card to charge the transaction and do the transaction. And if it can't figure out how to make the purchase, we might say, well, the problem is it doesn't know the credit card number, or it doesn't know how to use a credit card. And so Newell was pointing out, and I think also Dennett, that we use these words like know and goal. When as engineers, when we're describing systems, we say, "Oh, I see. At this point in the program, it doesn't know the IP address," and so it seems that it's very useful to describe what a system knows, and to then say, well, a failure of behavior is a failure to have the right knowledge or a failure to apply the right knowledge. I mean, we're seeing this right now with LLMs. I think a lot of prompting is about we know that the LLM knows some fact, but how do we prompt it so that it will use that fact to answer the question? And I think a lot of this chain of thought stuff is all about trying to elicit the right knowledge out of this giant sort of latent knowledge base that's somehow inside these systems, so that they can use it to do things. But okay, so that was the picture. Was Newell was trying to describe systems, and it occurred to me, well, we've been trying to define what does it mean to learn, right? This is again pre-statistical learning. So what it means to learn is that a system goes from having some amount of knowledge K1 at time 1 to some larger amount of knowledge K2 at time 2. And so if we could quantify that knowledge and describe that change in knowledge, that would be learning. And so that was my attempt. And one issue that always comes up is when you're just saying, well, does a system know something? What if a system knows, the classic case would be something like, it knows all men are mortal and it knows Socrates is a man. So does it also know that Socrates is mortal? Does it know the logical consequences of its existing knowledge, which we might call the deductive closure of everything it knows? And there was, at one level, you might say, yes, the system, at least if we give it an infinite amount of computational capabilities, then a system could compute all of the consequences of its knowledge. But in practice, of course, the system can't afford to do that. We live in a finite universe, and so it might implicitly know something, but not actually be able to compute it in a reasonable amount of time. And this leads us into the whole field of computational complexity and all these kinds of things. So there was so I wanted to draw a distinction between symbol level learning, which was appealing to another Newell and Simon notion that there's a level of description of the system called the symbol level, which is just below the knowledge level, and in which you might be doing things like computing the logical consequences of your existing knowledge, and then caching them away so that they're immediately accessible if you need them later. Newell had been working with Paul Rosenblum, his PhD student at the time, on a theory of skill acquisition, which modeled the acquisition of human skill through practice as exactly this kind of phenomenon. You're told, say, the rules of chess, and so in some sense, if you know the rules of chess, you know how to play all possible chess games. You know who wins. You know whether white can win or whether the value of the game is it's really a draw. No human knows this, no machine knows this, but this is, of course, it's a logical consequence of the rules of the game. Well, but you don't know how to play the game very well, and so as you practice, as you play many games, their theory was you are basically learning patterns that are the logical consequences of what you already knew, but you're then storing them so that you can recognize them and use them quickly in the future. And they showed that this explains the power law of practice, which was something that's a pretty robust finding in psychology, and several other things. Anyway, so I was calling that symbol level learning because in some sense, the deductive closure of your knowledge has not changed, but the computationally accessible amount of knowledge that it has changed. It has increased as you do this. And there was a sub area of machine learning that had been born around this time called explanation-based learning. And it was precisely this kind of process. You would learn how to say the first example was a system that learned to solve problems in integral calculus. And what it would do is it would start out with just the basic rules that you find in the CRC integrals table or whatever. And given a problem, it would engage in a search process similar to A star search to try to find a sequence of integration operations that would solve the problem. And then it would analyze that sequence and say, what other problems would this same sequence of operators apply to? And it would try to find the so-called weakest preconditions of that sequence, which would be, and then it would store a new pattern, a new integration rule, and it would say, for anything of this form, you can apply this as a macro operator and get the answer immediately. And so it could learn these over time. But it was really just working out the logical consequences of what it had already been told. And this was somehow very different from what was happening in inductive learning or statistical learning, where we're only told a finite set of data points, and we're trying to leap to a general rule. And that goes beyond the evidence, right, to some higher level. Now, the standard Bayesian view of this is that it's not actually an inductive leap. You have a prior, and you're just updating that prior with this evidence, and now you have a posterior. And the posterior is a deductive consequence of the prior and the evidence. So the Bayesians kind of avoid this problem of induction by turning it into a statistical inference. But in my paper, I was looking at things like these decision tree algorithms and so on, which are really using some form of Occam's razor. And so they've adopted some space of hypotheses, which might be logical rules with at most 5 conditions. And then they try to find the simplest logical rule that is consistent with the data, and then output that as their new belief and try to act on it. And so they are making some sort of a non-deductive substantive inference from that. And so that's I was calling that out as a different kind of knowledge level learning, because it seems to be involving this inductive leap. So that was really, I was trying to really say, those guys that are doing this explanation-based learning, they're not solving the problem of induction. This is all a side show, and we should be focusing on the real problem, which is statistical learning.
The problem or the example of this symbolic integration solver that you had was pretty interesting there. And I suppose for somebody listening to this, trying to make sense of it a little bit more, it's not too different from experiences we might have in, say, doing mathematics. I had two friends who took analysis classes in college with pretty different professors. And one of those professors was running their analysis class in such a way that they were really rigorous about every proof and kind of trying to solve everything from, the most basic principles and the ground up. And that class went really slowly, but then, this student got really good at proofs, and then the other took one with a different professor. And so they both took analysis two together. And one of those friends who took the class with maybe fewer big hammers and theorems and tools was like, I can do all the proofs, but I'm so slow at them compared to the other students because they have all of these theorems that, I mean, I can in principle prove from what I know, but they can just kind of like whack at things and get to the solution faster. And he felt like he was suffering a little bit there. And so it's like, yes, in a sense, like there is that same deductive closure aspect that you're talking about, but in one case, you do have something that is a serious difference. You can get to the thing you want to do a little bit faster.
Right. And I think when we now look at what's happening in large language models, there's a sense that they seem to be learning what would be kind of the results of inference without having learned the first principles, right? So they don't have a causal theory of why certain things are the right answers to questions, but they've kind of memorized these patterns without the ability to derive them, so this also relates to the system one, system two notion, right? That system two is more this. Let's prove things from deeper. Not we somehow our first taught the rules of chess, and then and when we first play chess, we're playing with system two, and it's very slow and interpretive. But over time, we turn that into a practiced skill and becomes kind of mental muscle memory, and it's now system one type knowledge. And Rao Kampampati at Arizona State and I have both been, several other people have been pointing out that it sure feels like LLMs are just learning straight at system one without ever learning the system two knowledge in a way that they could do the skill acquisition. And as a result, they don't get faster over time because they don't have a skill acquisition component. But I think that's maybe also relevant to this question of the role of metacognition, right? There's this paper by Mahawald et al. That came out, I guess, in 2022 about analyzing LLMs from the point of view of neuroscience, cognitive neuroscience. And they point out that one of the roles of the prefrontal cortex is to know when you're in a novel situation where you can't rely on your system one knowledge and you have to go back to working with your rule-based knowledge. And I think that's something that's missing from large language models, and sort of all falls into this story about skill acquisition, deductive knowledge level versus inductive knowledge level learning.
Right. And again, I guess as you kind of mentioned earlier, it's not that they're just totally incapable of doing something that at least looks like step-by-step reasoning. And, you might have intuitions about what's actually going on when it appears that they do that. But we do have to take pains to elicit that out of them via things like chain of thought prompting, like in the case of doing arithmetic. Hadi Zhou, for instance, had that paper on algorithmic prompting to get them just to do, well, addition, multiplication, that sort of thing correctly as well.
Right. They certainly are not learning how to add and multiply the way human students do. One of the people on my PhD committee was Kurt Van Lane, who was developing a sort of inductive theory of how children learn to do multi-column arithmetic. It would be wise for people to go back and look at that, because his premise was that the title was something like one disjunct per lesson. The idea that the student is expecting that each has a sort of prior bias, that each lesson is going to teach a new branch in the program that we need to learn, and so that allows them to very rapidly learn learn the program. But yeah, I mean, there's presumably a vast amount of stuff that we learn as humans for which we do not have the system to rule basis for it. We just learn this works, right? And this also leads to superstitions. My wife was a lab scientist, and back in the days when everybody was running gel electrophoresis and other things, there were all kinds of sort of magic steps in the lab protocols. No one knew why they were there, but no one dared remove them either. Because it works, right? And so, why do you soak this filter paper in milk before running the experiment? No one knew, but experiments are painful, so you just do it. So we get that kind of hitchhiking of irrelevant beliefs along with because we don't have the ability to appeal back to the fundamental causal story.
Right. There's also ways, I guess, that kind of doing the reverse can lead us astray. Not to say that we live in a world where there aren't reasons for everything or anything, but you think about the ways in which we develop conspiracy theories and almost that being an over application of system 2 type thinking, or at the very least, you do that in such a way that it leads you kind of down a wrong path. And there was a really interesting paper on one way you might suggest or think about this happening that I read recently. One of my professors in college was very interested in the principle of sufficient reason in metaphysics, just that for everything that exists or obtains, there is a reason. And this paper was sort of looking at how that maps onto human cognitive systems. Of course, Kant, for his part, was also very much like, human cognition is going to look for basic grounds for all sorts of knowledge. And I think that this paper was looking at, well, in our sort of daily acts of thinking about the world and reasoning about things, does something like a principle of sufficient reason apply? And in the experiments they did on human subjects, it did seem like something of that sort was going on, where people would seek reasons for things. But I think that, to what you said, I guess, in the reverse of the system 1, system 2 thing, maybe it's not entirely a reverse, but, we look for reasons where maybe it's just very, very difficult to find them or something of that sort, and then kind of end up in these jet fuel can't melt steel beams kind of ideas that lead us astray in a lot of cases.
Yeah.
I'd love to move on to a couple of your papers on, I guess, what you called sort of routine science. And the first section of them is a lot of earlier work on ensemble methods and machine learning. And one of the first ones here was on solving multi-class learning problems via error-correcting output codes. There are really, I think, kind of two key aspects of this approach, but I think the maybe most interesting idea here is just the maybe framework we kind of have for thinking about these problems in this paper. So I'm wondering if you could maybe introduce some of the ideas here.
Well, so that paper partly had its origins in the fact that I had a colleague in the office next to me who works on error correcting coding, and so we would chat. But let's say you have a classification problem. I was very much inspired by the early work that Terry Sinofsky published on the NetTalk system. So one of the early demonstrations of backpropagation and sigmoid neural networks, right, was a system that could learn to convert from spelled English words into their phonetic transcription. And then you could push those through a device called the DECtalk, which used a phonetic input and would produce speech, synthetic speech in various voices. And it was a fun demonstration of learning because it basically studied a phonetic dictionary, of I want to say 20,000 words of English and their phonetic transcriptions, and then it could pronounce words that it had not seen in the dictionary. We held out a test set of things. And one of the things that was interesting there was that they represented the output phonemes not as, I think there were 55 classes of phonemes, but they represented them using a distributed representation in terms of properties of the phonemes. Were they ones where there were like sibilates or plosives? The kinds of attributes that phonologists and linguists talk about. And so that meant that instead of having, if we have 54 phonemes, having a neural network with 54 outputs, the network had many fewer outputs. and was encoding these. And I thought that's interesting, and I saw this analogy to error correction codes where if we have a discrete vocabulary of, say, 128 things we want to encode, we could encode it in 7 bits, but then if we're sending those 7 bits over a noisy channel, every code word, if it's mutated by flipping a bit, will turn into another valid code word, and you can't correct it. But if we add some check bits or parity bits, then we can ensure that around every code word there's like a ball of Hamming distance 3, say, and that means we can actually recover from any single bit error. And so that was the idea, was that since learning algorithms are imperfect, and we could maybe think of the learning algorithm as being like a noisy channel, so that we're going to formulate a whole set of binary problems that correspond to the individual bits of a code, of an encoding, an error correcting encoding of the original K-class problem. So if we had 128 classes, we could have 7 bits that were the original 7 bits that are encoding in binary the problem. And then we could add another, with neural networks, we could put 30 or 40 extra bits and so we could use error correcting codes that have huge correction capabilities. And so now we're training a bunch of 2-class classifiers and hoping that they make independent mistakes. If their mistakes are made independently, then basically, the binomial theorem applies, and we can guarantee that we can correct the vast majority of the errors. And so it turned out that it worked. Now, soon after that, other people developed other ensemble techniques. In particular, random forests were, Leo Breiman's great contribution. Also, boosting techniques, bagging, and these could all be hybridized. So it turns out that you could combine boosting with error correcting codes, or bagging, or random forests. An interesting question that we might want to think about is our deep learned representations, that these embeddings are, maybe do they have some error correcting behavior? Are they separated enough in the latent space that if some feature detector in the encoder maybe makes a mistake, it still more or less gets mapped to the right word? Certainly with something like attention, you could imagine that you're decoding that into something that's more like the closest code word in the space when you minimize, say, the dot product or the cosine distance. So so maybe there's another lesson there. I don't know.
So maybe an experiment for what you're mentioning there would look something like, basically along the lines of what you mentioned. So if a feature detector makes a mistake, maybe you can go and intervene somewhere in the network and mess with some intermediate representation somewhere and kind of see what comes out the other end.
Well, I guess you'd be looking for redundancy. So one of the things about error correcting codes is that they are not information bottleneck minimizers of the channel. There would be some mechanism that's deliberately introducing redundancy, and I don't know if there's any such mechanism happening in these systems. But we also see weird kinds of things. My colleague Fuxin Li and Alan Fern developed this work in explainable AI, where they were trying to look at single neurons or units in the, say, output layer of a neural network, and ask, well, what are they? What was the meaning of this neuron? And what they found is that meaning is often overloaded. So they were looking at the Caltech birds data set, and they would find that a unit could simultaneously be encoding some pattern that might be true of the beak of a bird, and also some pattern that might occur on the tail of the bird. And the thing is that very often in most images, only one of those 2 parts of the bird will be visible. And so the same unit can perform 2 different functions. So I don't know whether it could be that the learned representations are actually extremely compressed, and that they're not learning any kind of redundancy. This would argue that kind of experience with the bird data set suggests that they're trying to pack as much information into as few units as possible, which is one of the reasons we have difficulty understanding what they're doing.
Before we move on from this paper, you had this open question at the end, which you've touched on a little bit, but this was about why does the error correcting code method work in the first place? You brought up the point that it, well, does seem to work, and our hope that the different classifiers make independent mistakes seems to kind of hold up. But your intuition there was because the hypotheses are learned using the same algorithm on the same training data, then you'd expect some high level of correlation and that the errors couldn't be corrected with such a code. So I guess I'm curious if there's been follow-up work on that, or if you've maybe developed other intuitions about what might have been going on there, why the intuition doesn't seem to coincide with what happened.
Certainly one thing is, if I were revisiting that now, we know that, well, and I kind of discussed it there, we know that the data typically underdetermine the answer, right? So there are many different, say, decision boundaries that are consistent with the data. And so if I'm using independent learning runs of the learning algorithm to learn each of the bits in a distributed output encoding of the class labels, we might expect that they're making more or less arbitrary choices among the equally good fits to the data. When we use so that gives them some independence. I mean, the other argument that we made in that, we had a follow-on paper where we looked at thinking about it in terms of the actual structure of the decision boundaries. When I define a Boolean, one bit in the error correcting code, I can think of that as actually defining a set of classes. If we were thinking about something like the MNIST digit recognition task, one bit might be is the digit odd or even, and another bit might be is it 1, 2, 3, or 4 versus the other bits. So each one is asking a different question about the data, and its decision boundary may be again what classes you group together will change the required curvature of the decision boundary, and may make it easier or harder to learn that concept. And so that's another way that defining the set of binary questions maybe perturbs the algorithms. The general notion of any ensemble method is we're trying to introduce some perturbations into the learning algorithms in order to make them make independent errors that then we can average away by some sort of central limit theorem type of behavior, right? And so at least that was the story at the time. I mean, we might, in light of this benign overfitting phenomenon we see in deep nets, where we perfectly fit the data and keep training, and our accuracy, our generalization error continues to drop, even when our training error has already hit zero. That's calling into question whether this pure bias variance explanation of what was going on in ensembles still applies, or whether there's maybe something else we need to think about.
Yeah. Another interesting thing that we see sort of going on in modern transformers that feels kind of related to your explanation, of course, not precisely the same, is that in understanding what's sort of going on in different heads of a transformer, when people have done evaluations on those and looked at what's going on with the purpose of figuring out, well, maybe what sort of syntactic relationships are being encoded in the representations of these transformers. And they might find something like, well, different heads are actually encoding different syntactic or grammatical rules. And so it's maybe not exactly the same thing as what we're going after here, but it does seem like maybe a sort of related phenomenon that's going on.
Right. In some sense, that we're trying to decompose the problem into a set of simpler problems.
So I think maybe for not spending too much time on this section, but quickly moving on, you did have another paper on ML bias, statistical bias, and statistical variance of decision tree algorithms. And just for the purpose of maybe pausing on the idea of bias for people who are kind of listening to this, I think there's maybe a mix of backgrounds. And bias, of course, is a really overloaded but important term in machine learning and in learning theory in general. And I think for me, when I was getting introduced to this, I like the idea that the learning from data book kind of introduces pictorially with, reference to hypothesis spaces and optimal hypotheses. But if you could introduce the term bias just for the first time to somebody, I'm curious how you would approach the discussion.
I mean, I usually would draw a picture, but the definition of bias from a statistical point of view, right, is that the prediction that the algorithm is making is systematically off in some way. If we're thinking about regression problems, for instance, it might be systematically high or systematically low, and that's different from, say, the bias that might be against some one subgroup of people versus another, like the bias in image recognition for face recognition, that the system just performs more poorly on darker faces. And that then lines up with a cultural bias that's about fairness. But this notion of statistical bias is that if we think about just regression problems, so say linear regression with least squares, we can decompose the error of a regression model into two terms. One is the variance, just how much every time you run the algorithm on a new sample of data, you'll get a slightly different fit to the data, right? So if you imagine you could draw 100 independent training sets for a problem and fit 100 different linear regressions, they would all be similar, but if we graph them all, they would be like a cloud of lines, right? That would be vibrating around in some sense, and the amount of variation from one line to another, that's considered to be the variance of the algorithm. The bias is if we now took the average of all those lines, is that line systematically off from the true regression line? And that would be the bias. Now, a lot in statistics, there for many years the goal was, let's find an unbiased estimator. We want to have an unbiased estimate of the regression line because we want to then interpret it, say, causally or something like this. And we're trying to estimate, say, the causal effect of giving aspirin or something. If we get a biased estimate, we're going to under or overestimate that effect, and that would be bad. But when we once you step out of the maximum likelihood view of the world, and particularly in machine learning, as we go to extremely flexible collections of hypotheses that have, say, varying levels of complexity. So the simplest thing would just be if we're doing feature selection in regression. But more generally, with decision trees, how deep do we grow them? With neural networks, how big do we make the hidden layers? We end up introducing a huge amount of variance in the models if we use very, very large models. And so typically we put in some form of regularization, which will reduce the variance, but usually increases the bias. So what's, I guess I'm trying to think. Anyway, the one theory for what was going on with, say, bagged or ensemble methods in general, but particularly bagging and randomization techniques. So in bagging, we would train. We don't expect to get actually 100 independent training sets. We get one training set, but we can use what's called bootstrapping to draw subsamples of that data set and train the classifier 100 times on 100 different random subsamples of the data set, and then have those vote. Now, when we train on subsamples, we actually are increasing the variance, but when we vote them, that's a variance reduction step. And typically, the variance reduction that we get would really greatly improve the accuracy of the answer. But it might also risk slightly increasing the bias. So, but the sort of the game that we're playing in machine learning, I think, is that if you use a very flexible space of hypotheses, then you bias is not your problem. You can represent the right answer. So that's not the problem. The problem is that you increase your variance. So by using a very flexible hypothesis space, but then creating ensembles and voting them, you can squash the variance, and that's how you get a big win. So that was the idea and that was kind of a tutorial. So the question was, okay, that's a whole story for squared error. But in machine learning, we're usually doing classification. So we're using 0-1 loss is really the loss we care about, or we're using log loss, cross entropy, or something like that instead. And now, is there a way to draw the same? Can we bring the theory over and have something like, a bias is very straightforward, because the bias just asks, is there a systematic error that's caused by your learning algorithm or your space of hypotheses? But variance is a little bit trickier to define, and actually it's not that hard to define either. You can define the bias and the variance. The problem is you can't decompose the ultimate 0-1 loss into just a sum of bias and variance. You have to introduce an additional term, which in my paper I tried to define it away, but that was a hack. And one of Trevor Hasty's PhD students, Gareth James, as part of his work, really I think it did the definitive work of defining an additional term that he calls the ensemble effect, that gives a clean decomposition, and then he's able to use that to give a good theory of why these ensembles are working.
Let's talk a little bit about reinforcement learning before we finish up this section. And there are mainly two papers I want to discuss here. One of the ones that you're very well known for is MAXQ for hierarchical reinforcement learning. To begin with, maybe for the uninitiated, could you explain what hierarchical reinforcement learning is?
Well, so we know that obviously reinforcement learning, we can view it as in some sense the learner is learning a program for behaving in some problem, for playing Atari games or chess or whatever, and maybe in chess it doesn't decompose, but we know in a lot of these games and in a lot of other real situations, it's just as in ordinary programs where we often decompose the program into subroutines. We want to think about it in terms of a set of subgoals. So if I'm building a system that's a personal assistant, and maybe it's trying to arrange a wedding, let's say, then it's got subgoals like find a venue, find a caterer, find musicians, both for the ceremony and also for the dance, and on and on and on. All of these things, who's going to provide chairs and tables, and so those are all different subgoals. And if you just flatten that as one big reinforcement learning problem where it has these dozens and dozens of actions it can take and some reward function at the end that just says you have a successful wedding and everybody leaves the party happy, whatever. I don't know how you form a reward function there, but it's going to be very hard for the reinforcement learning system to solve it in that sort of very flat formulation. You'd really like instead to be able to decompose the problem into subgoals and then have reinforcement learning apply at the subgoal level, and then somehow take the reinforcement learning solutions to the subproblems and glue them together to get a reinforcement learning solution to the whole problem. And so, at the time I wrote that paper, there were a couple of other proposals for how to do this, and not so much how to do the decomposition, but if someone gave you a decomposition into subgoals, how could we do reinforcement learning in a way that could take advantage of that decomposition? So Doina Precup and Rich Sutton developed this thing called the options framework, which basically showed how you could introduce macro operators basically into a flat reinforcement learning system and have it work with those. My approach was maybe more of a programming, software engineering kind of view, which is let's decompose we will actually rely on a programmer to decompose the problem into subgoals, and define rewards for those individual subgoals. And so when we think about the reward for the whole wedding, you can think about how you might decompose that into rewards for the individual parts. And actually, reward functions often do decompose into different concerns that you want to have different rewards for. And so that paper was about a nice formalism that said, well, what does it mean for a policy to be optimal in this hierarchical sense? It could be that it was optimal for the original flat MDP without the hierarchy. But often when you introduce the hierarchy, you no longer can express what the original optimal policy was, because if your policy is restricted to solving these subgoals sequentially one at a time, then I define a notion of hierarchical optimality, which is, it's the best policy out of all policies that can be represented in this hierarchy. And then you can even make a further thing, which is sort of it's kind of locally hierarchically optimal in the sense that that each subtask is being solved optimally, but that doesn't necessarily apply that the overall task is being solved optimally. So, and then I developed a learning algorithm for if you were given that hierarchy for learning. And what was interesting was that learning was not faster out of the box. What allowed us to actually get a speed up in learning was if in the subgoal you could ignore parts of the state variable of the state. So when you're thinking about planning for the band or something, you do not have to worry about who's providing the tables and chairs, or so you can ignore big parts of the state space, and that's when you get a big win, right? Because the curse of dimensionality is the curse of high dimensional state spaces. And so what was the surprise? It was a surprise to me when I was working on it, was that it was by introducing the hierarchy, you could define subtasks where only a subset of the state variables were relevant, and that gives you the speed up. It wasn't the hierarchy itself that gave you a speed up at all. In fact, it could make things worse. But if you could rely on it to shield you from some of the state variables, then you got a big win. So that actually then carries on to this exogenous state MDP, because now 20 years later, or 18 years later, in a collaboration with my colleague George Tromponius, who at the time was working for Huawei, we were looking at the problem again of how can is there a way we can ignore certain state variables in a problem? We were working on a problem for Huawei that involved controlling cell towers, right? So Huawei sells cell tower systems, and a cell tower, it turns out, can be reconfigured in real time. You can move the antennas around, and you can change, 50 or so parameters of these things. And they thought, well, let's formulate that as a reinforcement learning problem, sort of maybe naive, and we'll just solve it. But the problem is that what is the reward function? Well, the reward function is something like the fraction of customers who have adequate bandwidth, and what determines that? There's an awful lot of things customers are doing that are outside of the control of the cell tower operator that are going to influence that. Like if all the customers all go to a football stadium, and we just don't have enough cell towers there, or during rush hour along highways, maybe there's just not enough capacity. We're going to do badly on our reward, and of course the reinforcement learning algorithm is going to sit there tweaking these parameters and seeing if that makes an improvement in the reward. And the truth is, nothing that the reinforcement learning algorithm is doing is going to improve the reward in those situations. I mean, our big realization was in the middle of the night when there's no demand, reinforcement learning won't be able to learn anything, because nothing it does will make any difference, because there's no customers, so they're all happy. And in rush hour, same thing, all the customers are unhappy, but there's still nothing that the learning algorithm can do. It was only on the shoulders, on the margins, where the controller could actually do something that would make a difference to the customers. And so we realized that the state of the system included all of these exogenous variables that were not under the control of the cell tower, but the reward function did depend on those variables, right? That was the challenge. And so we studied this problem, and we had a short paper at ICML 2018, and now we have this long paper on arXiv that's under review, where we work out a very comprehensive theory of exogenous variables in MDPs, and for the special case where the reward function can be decomposed as a sum of some terms that depend only on the exogenous variables and some terms that depend on all the variables, then we can show how you can simplify the reward function and remove variables from the reward function. And if you do that, then again, you can get a big speed up in learning because you have a simpler reward function, a lower dimensional reward function. Yeah. And it was quite surprising in those experiments. We found that if your action space only, say, is 3-dimensional, you only have 3, say, real valued parameters you can set in this thing, then the endogenous space, the reward function that you're working with, can be reduced to a reward function that depends only on 3 variables. So so you get amazing reductions in dimensionality as a result of that theorem, basically.
I think this exogenous way of thinking about things is going to come up again when we talk about robustness a little bit later, from what I recall of your coverage there. And maybe as a way to bridge us there, we can talk a bit about your work in computational sustainability. And here there's been a particular project that you've been involved with called Project TAHMO. Perhaps you could introduce that, and then we can talk about some of the goals and research challenges in ML for computational sustainability.
Right. So, as a sort of lead into TAHMO, I've been working since the mid-90s in collaboration with ecologists here at Oregon State. Oregon State University is one of the real powerhouses in ecology, in forestry, fisheries, atmospheric sciences, oceanography, and so I've had many collaborations on all kinds of projects in wildfire management, invasive species management, all kinds of things. But the TAHMO project, and so I like to think about computational sustainability as a kind of a whole pipeline that starts with where do we put sensors if we're sensing the environment to study something in an ecosystem. We need sensors out there. And then often the raw data needs to be converted into something more meaningful. Like, for instance, maybe I put out camera traps because I'm trying to measure wildlife. And now I get all these images or video. I need to do computer vision to turn that into counts of individuals and then fit machine learning models to that to build models of the ecosystem and its dynamics. And then ultimately, maybe I now want to introduce a sort of Markov decision process problem of, okay, now I want to intervene in this ecosystem to maybe kill an invasive species or reserve habitat or whatever. So now I'm looking at policymaking, and I need to solve MDPs or POMDPs or something. And so computational sustainability can enter at many different places in the pipeline. TAHMO is the Trans-Africa Hydrometeorological Observatory, and it's an effort by my colleague John Selker, who's a hydrologist, and another hydrologist, Nick Van de Giesen from the Technical University in Delft. They've been working for many years in Africa. John was a Peace Corps volunteer there as a young man. And one of the things that is holding back agricultural productivity in Africa is the lack of good weather data. In the United States, the National Weather Service is estimated to contribute indirectly many billions of dollars, something like $20 billion of GDP, because it gives good forecasts that can allow farmers to make planting decisions, harvesting decisions, crop insurance decisions. It supports the whole futures market. And so this is lacking in large parts of Africa and Latin America, where you talk to anyone who works for a National Weather Service, they'll say they're underfunded, even in the United States, but they are woefully underfunded in developing countries, of course, because there's just not, government just doesn't have a lot of funds to work with. And things like education and water systems take priority. So they also, because of the huge progress in miniaturization, we can go from weather stations that cost tens of thousands of dollars to, say, a $1,000 single unit that can have a weather station in a very compact package and be fully automated. And so their idea was, could we build a weather network in all of sub-Saharan Africa that can transform Africa from being the worst sensed continent to being the best sensed continent. And so that's their sort of moonshot. We're not there yet. We have a network of about 700, actually 750 stations, but we only count 650 of them because a lot of them are offline these days. And we're in about 22 countries in Africa, which in and of itself is a huge accomplishment because we had to negotiate a memorandum of understanding with every government that we would be allowed to operate in that country and that we would be allowed to take data out of that country. And of course, this involves sharing the data for free with those governments and their meteorological services, really trying to support their meteorology offices. And so the most of the funding has come from things like USAID, the United Nations, the EU, and now some is coming indirectly from things like USAID or World Bank funding countries to improve their infrastructure, and then they turn around and hire us to do their weather infrastructure. We also have some funding from IBM and from Google, as they have been interested in weather data at various points. So my role in this project is sensor data quality control. So I like to joke that these weather stations are fantastic if you keep them indoors in the laboratory, but for some crazy reason, we want to put them out in the environment. And so, an important design goal with these weather stations is no moving parts. So, you don't use a tipping bucket rain gauge anymore because the tipping bucket can jam. You don't use a spinning cup anemometer because it can jam. You use ultrasound instead. But unfortunately, rain gauges in particular, you still have to measure the rain itself. So the moving part is the water. And precipitation has become my number one headache because it's a very non-Gaussian behaving variable. It's zero most of the time, even in very wet places. And it's very heavy-tailed. And yet it needs to move through our measuring device. So the collecting cone can get clogged so that the rain gauge is reporting zero incorrectly when it was raining. And also the entry to the rain gauge can be open, but the exit out the other end can get clogged. And then the water backs up and leads to absurdly high reported measurements, like 2 meters of rain. And we don't think 2 meters of rain fell on there. So my original dream was that we could use statistical methods, off-the-shelf machine learning. One of the goals of machine learning, I would say, as a field has been, can we develop these very general-purpose algorithms like random forests, right, or these gradient boosting techniques that can be pretty much applied out of the box without any hyperparameter tuning to any random problem and get decent results. This is sort of Leo Breiman's vision in statistics as one of the, he was one of the co-inventors of classification and regression trees. And so I was hoping to use out-of-the-box kind of generic techniques to do basically anomaly detection, look for anomalous readings from our weather stations and flag those for the technicians to go visit the station and repair them. Well, and the alternative to this is to start doing detailed modeling. Build models of the time series behavior of rain or the spatial behavior of rain and things like this. And I had done work on anomaly detection, benchmarking, showing that an algorithm called the isolation forest that was invented at Monash University in Australia by Kai Ming Ting and one of his students, and Jihua Zhou from Nanjing, that this was a really nice off-the-shelf anomaly detection algorithm, at least for featureized data. And so we deployed isolation forests on our problem, and it performed terribly. So over time, I've been forced to get more and more into modeling. to the point that now we are just working on trying to identify clogged rain gauges. We have a model just for that purpose. But we have models deployed on the network. They are detecting anomalies in the precipitation values. Then those go through a human review and turn into trouble tickets that the technicians then go out in the field and fix things. So we're continuing to develop better models. This clogged rain gauge one we hope to deploy later this year, and we have another model that we're working on that might be even better. So it's been I don't know. I feel like I've had to sort of leave behind the goal of off-the-shelf machine learning as a solution here and get my hands dirty doing detailed modeling. And I think when you do application work, you often are forced into this. So you can't just point a large language model at it and say, look at this rain.
Yeah. I guess often are the assumptions and theories we want to make also tend to fall apart the moment we encounter the real world in a lot of these cases. This is maybe a good lead-in for us. We can quickly so this has sort of demonstrated a couple of the problems that you talk about in terms of the distinctive characteristics of sustainability problems. In this case, particularly about just how tough the data can be to work with. And I think that you've also sort of touched on a couple of the other issues that sort of come up here and the other projects as well when we're thinking about policies for controlling invasive species or these sorts of things. And that we typically have these goals that are to maybe deal with spatial spread in one way or another. And also with when it comes to optimization, we actually do have robustness as a concern. We need to be robust to incorrect models. We need to deal with unknown unknowns. And I think that the idea of unknown unknowns is really one of the central features of the president's address he gave on steps towards robust AI. The idea that really we can't model everything and we have to accept that as a fact about the world. And I think that robustness right now is really important and kind of a central topic in a lot of ways, especially as we're thinking about some of the failures of large language models. A lot of AI safety people are very concerned about things like misspecified goals that come up in robustness as well. Could you perhaps introduce some of the way that you've thought about robustness recently and the different types of problems we have to encounter in that space and how we sort of think about them?
Right. So as I said, I've been interested in anomaly detection because that's my main thing. So when we build, say, a machine learning system, I think every machine learning system should have a model of its own competence. It should know the subspace of the input space for which it's able to be trusted, and outside of which it should not be trusted, right? And so the question is, well, how can we build those competence models? So one thing, of course, is that if we're assuming that we don't have any distribution shift, and so we're just dealing with IID data, then we can look at getting calibrated uncertainty estimates out of classifiers. And so I've been very interested in the calibration literature. I'm a big fan of conformal prediction, which gives us very nice finite sample guarantees that are quite tight. And so those are wonderful. Of course, every real application problem encounters distribution shift. So then the question is, well, how can we deal with that? And I have not worked on this too much, but obviously there are many people doing very nice work on detecting distribution shift, and then building systems that are either robust to it in some sense. In particular, looking for invariant models that are invariant to distribution shift, and also doing things like transfer learning or adaptation under distribution shift, domain shift, things like this. So I'm very excited by those. The problem that I've really focused on, though, is known as the open category problem or the open set problem, right? In computer vision in particular, this arose in another one of my sustainability projects, which was measuring freshwater health or the health of freshwater streams. is done using bioindicators. So the US EPA every year does a randomized sampling of the insects that live in freshwater streams in the United States. So it turns out there are many species of insect that spend the majority of their lives in a larval stage as a bug living underwater with gills. They typically only emerge from the water and fly around and breathe air just long enough to mate. And then they drop their eggs into the water or lay them on leaves or whatever, and their lives are over. So stoneflies, mayflies, caddisflies all have this kind of life cycle. And so that testing problem, they collect these samples and bring them back to a laboratory, and then some technician has to go through and pull out each insect and classify it to at least the level of its genus. And then they count these up, and because the different genera or species are vulnerable to different pollutants, you can look at a histogram of what species were present there, and it's like a fingerprint for what kinds of pollution the stream has been experiencing. And the beauty of it is that because those insects are living in the stream for a long time, they're integrating this information over time. So it's not like a single point in time chemical capture where maybe a polluting company upstream knows you're coming and they close the pollution off for a few days and you miss it. The bugs know, because the bugs have been there the whole time. So I had collaborators, and we who actually initiated this project. We were using state of the art for the time, which was support vector machines over bags of SIFT features and things like this. But we got a system that performed quite well on 54 different species or genera of these insects, but we had focused only on the species that were of interest to us for this health measurement problem. But the real field samples that you get, it turns out there are 1,200 species of insects in the United States, not 54, which were the 54 that my system could handle. And so it was only as we were getting ready to deploy it that we realized, we have this open set problem. We have to detect these other things that are not our species of interest. And we found that we were achieving an equal error rate of 20%, which is to say 20% of these aliens, let's call them, we were incorrectly recognizing as one of our classes of interest. And 20% of our classes of interest we were rejecting as being aliens. So this was unacceptably poor behavior. It just wasn't usable. And so that's what launched me on this whole goal to develop anomaly detection algorithms that could detect that these things were different from my training data and that I should reject them as being anomalous. So that's my strategy for trying to deal with the unknown unknowns. So we've been working on this for a long time. What we've discovered just in the last few years, because we're just coming off of a grant we had from DARPA on this, is that deep anomaly. So anomaly detection, when we do it sort of with traditional techniques where we're hand engineering the features, like if you think about the famous irises problem that Fisher used when he was developing Fisher linear discriminant analysis, you measure things like the length of the sepals and the lengths of the petals. And if you have a species that has sepals or petals that are much longer or much shorter than the ones in your training data, they are obvious outliers in your feature space. Okay, and so these anomaly detection algorithms can find them very easily, and it works great. But when we go to deep learning, now we're relying on the learning algorithm itself to learn its own features. And it basically only learns features that detect variation that was present in the training data. For example, in my insect problem, we looked at the 54 categories that we were interested in, and we said, well, color is not an informative feature here, so we won't use RGB, we'll just use grayscale. But if there's 1,200 species out there and some of them have bright red dots, we won't be able to find them because we didn't include color in the features. It's just like, again, it was a whole mindset that you've got to, if you're doing robustness engineering, you need to think about all the other stuff, these unknown unknowns. How am I going to detect them? and it starts with your sensor data that you're going to choose. But back to deep learning, if your training data, if everything was the same color, then it doesn't need to learn a color feature, right? So it will essentially do the same thing we did because it's not forced to learn it. It doesn't carry, it's not useful for minimizing cross entropy on the 54 categories on the output. So it will not learn feature detectors for that. And so one thing that's interesting is, the self-contrastive, I guess instance contrastive learning like SimClear. Color there, it's a little tricky because, again, if you only have your known species and you don't introduce any like color perturbations to the data, then again, it won't learn to pay attention to color at all in its representation. So we still have these systems are still vulnerable to this problem, that if there was insufficient variation in the training data, then for instance with lengths of things, it seems that often the deep learning representation is more like a histogram style representation. So we'll have features that turn on for sort of small, medium, and large. And if there's something that's extra large in the test data, it'll just call it large. And it won't show up as an outlier because that's a large is a normal level. So again, we have a problem that we have to somehow get these systems to represent the space around the data, not just the data itself. One way to do that, I think, the most obvious thing is train on as much stuff as you can. So Dan Hendricks and I, right, had this paper on outlier exposure, and the idea was let's get a whole ton of unlabeled data that it doesn't even need to be related to the task at all. It's just more variation, and train our system to output low scores, low probabilities on all that stuff. But that does encourage the system to come up with features that let it separate this chaff, this junk from the classes of interest. And I think again, if you train on all of ImageNet, you have 1,000 categories. Maybe you're only interested in 5 of them, but you will have a much better classifier. And my former student Alex Geyer and I have this paper where we show that training on more classes, even if you don't care about them, but you have supervised labels for them, that's even better because you're forced to learn features to discriminate your known classes that you care about from lots of other stuff, and that lets you represent other stuff. Because if you can convert the problem of one of detecting outliers outside the feature set to just detecting unusual combinations of known features, then you've solved the problem. But one of the things we found, so we wrote this paper on what we call the familiarity hypothesis. One thing that's been very frustrating about deep anomaly detection is that the simplest method, which is just looking at the logit scores of a cross entropy classifier, is highly competitive with fancy anomaly detection techniques and all kinds of stuff that we cooked up, including trying to use isolation forest and other things. And this was really conclusively shown by a nice paper that came out of Zisserman's lab at Oxford, where they showed that if you just did a really good job of training a classifier and then use the maximum of the logit scores, for new classes, that maximum is often lower, and so you can detect that. But they didn't. It was experimental. What we put forward the hypothesis that what's going on is that these classifiers have basically learned to measure familiarity. They have a bunch of features that turn on when they see familiar objects, and if enough features for a class turn on, then it classifies it as belonging to that class. And when the logit scores are low, it's because there just isn't much familiar. The familiar features aren't being turned on, and so it says, I don't see anything familiar in the image. And that works, surprisingly well. And maybe there's a route to success there, but I think it is easily attacked. So you could imagine if you have an image that contains both a familiar object and an unfamiliar one, the classifier will be very happy with the familiar object, and it won't see, I mean, let's say the elephant in the room is a new class that it's never seen before. It won't notice it because it's very familiar with this tricycle that's in the foreground. It gets all excited about it. So that's part of the problem. But maybe the solution there is to use something like SAM, segment all the objects in the image, and then ask it, does this look familiar? Does this look familiar? And then it presumably would segment out this elephant, and then the classifier would say, man, I don't have any familiar features turned on in that region, so something weird is there. So maybe that's the route forward. But that's, I think that's an important direction for trying to deal with unknown unknowns.
One interesting part of this too was how it was pretty counterintuitive to you that deep classifiers achieve excellent anomaly detection. And as I recall, your intuition was that, well, we are dealing with familiar or unfamiliar training samples X. And so you probably want to model directly the probability of that training sample X. And when that's low, you get an anomaly, but then deep classifiers are instead, well, they're classifiers. So they're modeling P of Y, the class, given X.
Given X, right. Yes,
exactly.
Right. And so in theory, they're throwing out everything about P of X. Yes. So right. So this is a case where writing down the math does not help you, because you say, well, the anomaly's got to be in the X space. I've got to detect P of X as being somehow, the very low. But I think the problem with that is that if you have an inadequate representation, then P of X you won't get a good model of P of X. That's the problem. And I got very excited about these normalizing flow type density estimators, because you think, well, gee, we could do like high dimensional density estimation using normalizing flows. Our problems are solved because we can just model P of X. But unfortunately, they don't do any kind of dimensionality reduction. So they have the old problem that modeling P of X means you're trying to model the foreground, the background, the noise, the imaging conditions, all kinds of stuff that is not relevant to the classification task necessarily. And so you're setting yourself up an extremely challenging modeling task. So, but of course, when you're doing anomaly detection, maybe the background matters. Maybe the imaging conditions matter. Maybe if I don't want to trust the classifier when it's operating in low light conditions or things like this, right? So it's very hard to see whether there's any principle that lets us do feature selection in unsupervised learning. I think maybe that suggests that the whole saying, well, P of X is what we want, maybe that's not what we want. And we should think instead about what are the threats to the successful functioning of the system. Think more like cybersecurity. What are the threats to validity, or safety engineers? What are all the potential harms or failure modes? And then how can I protect myself from them? So I'm very intrigued by the idea that we might be able to somehow characterize the dimensions of variability that are present in our data and assess them and say, we have insufficient variability in certain directions. Let's either synthetically or generate new data there with augmentations, or go collect new data to build out more variability in those directions. And maybe we can try figure out reduce the risk that a novel object will vary in a direction that we did not capture in our training data. So I think it's these kinds of engineering steps might help us there. I mean, fundamentally, obviously, there is no solution. We can't see an ultraviolet, so something that's novel in the ultraviolet we wouldn't detect as humans. So so we can't expect to fully solve this problem. But so I think it's some kind of a layered approach, as we were saying, where you can say, well, I can tell there's some object there, but I can't, because it's object-like, but there's nothing familiar about it. So therefore, maybe I better stay far away from it because it's something novel.
I think this is a good place for us to move on to some of your more recent commentary. And actually, I think I want to begin with some of your commentary on large language models first. and you gave this talk about what's wrong with large language models and proposing alternatives at the Valgrind seminar. Is that a play on Valgrind, by the way?
No, it's Valencia. So the government of Valencia in Spain, that's one, right, has a. I think the G is for graduate and the R is maybe for research. Um, they have several universities. I want to say five or seven, uh, and they're trying to create a more lively research community across those universities. Some of them are very strong research universities, and others are could use some help. And the government is invested in AI by mostly with graduate fellowship funding for those institutions. And I'm an external advisor, and so we have an annual meeting to review their progress, and we run a symposium, as part of that, where the students present their work, and they asked me to give a talk. But for the last year, I had been doing a study on large language models to try as part of something called ISAT, which is a group of volunteer academics and some industry people that do studies to try to influence DARPA's funding priorities. And so my particular goals in that study were to try to understand, what is industry going to be working on? What should DARPA be working on? What are the research priorities for large language models? So that's what led to this.
Okay, that's good context. The fact that I saw the name and thought Valgrind tells me I've been spending a little bit too much time with C++ recently, I think. So let's maybe get a little bit into the main question of this talk about what exactly is wrong with LLMs and what we should be building instead. And here I think that you do rehearse a lot of the flaws that people continue to talk about with LLMs. The fact that they're expensive to update, they can produce kind of unacceptable outputs, that they hallucinate, of course. And I think maybe one interesting articulation you gave during that talk was that they are not just knowledge bases as a database might be, but they're statistical models of knowledge bases. And of course, you would never use a statistical model of a database, as you say, to answer questions about the database itself, which I thought was a really interesting way of putting some of the issues we're seeing. But maybe as a way to kind of lead into how to discuss some of these problems and issues, the thesis here is that LLMs there's something wrong with them. And at the same time, though, for a lot of people, they are interesting. There are interesting and useful things to get out of these models. So maybe we can talk a little bit about the high level goals here. If LLMs are not the way, what's the end game here? They're not the way to what? What do you think is sort of the appropriate goal?
Well, I guess since my fundamental goal is AI, if I want to make a knowledgeable AI system, especially maybe a AI system that can act as an agent on my behalf, um, then I want a system that that knows its own limits, but and performs correctly, and that can deal with say problems that involve, say, reasoning and planning, um, and that produces, understands its a kind of social, cultural, ethical situation and behaves appropriately. So I guess that I would say that that's kind of the ultimate goal is, to build an AI system, and and of course people are trying to use LLMs to do this, and they're encountering lots of problems, and as you say, I think the number one, I mean, the thing that is most fantastic about LLMs is that it's really our first exposure to a system that is knowledgeable across the breadth of human knowledge, right? The big lesson I take away from it is that scaling up learning to the scale of all of human knowledge, or at least all of the written knowledge that we have, is a very powerful idea. And we, as we think about how to improve LLMs, we've got to be, any change we make, it has to support this kind of end-to-end learning that's been so powerful. That's completely unsupervised or self-supervised learning. Um, because that's the only thing that scales. So, as you say, I think one of the big problems with hallucination, I'm starting to really like this word confabulation, because it's the idea of sort of confusion and fabrication. Is exactly that. Although it's extremely knowledgeable, and we want to treat it like a knowledge base that we can ask it questions. So, back in the 80s, researchers in AI formalized the abstract data type knowledge base. It just has two operations, ask and tell. So you can tell it facts, and then you can ask it queries. And the idea was, if the query followed logically from the facts, then it should do the logical inference necessary to answer the query. Or obviously, if the answer was just already explicit, like in a database, it should just retrieve it. So that was sort of the notion. And of course, there are a lot of issues about what if you tell it something that contradicts something it knew in the past. How does it do belief revision? And there was a whole line of research there. But as a knowledge base, right, I would say the two big problems are, we can ask it things, but it doesn't give us the right answers, and we can't tell it anything, because there's no way. Paradoxically, we're using what was originally an online learning algorithm, like the perceptron algorithm, stochastic gradient descent, which was could learn in real time, to train these things, but now they are extremely expensive to update. But in any case, so we have sort of a defective knowledge base. So, and part of it is, as you say, I think they act more like probabilistic models of knowledge bases, in the sense that that when you ask them to answer a question, they can make up a plausible answer if they don't know the answer, or if your prompt doesn't trigger them to retrieve the relevant piece of the thing, they might actually have the right answer somewhere in there. And I was drawing an analogy to work that I've seen in the past by Lisa Couture in her PhD thesis on probabilistic relational models of databases, where those models were very useful for things like query optimization, because you could estimate the sizes of intermediate tables when you did a series of joins. You could also use them to do anomaly detection on data elements. So if you saw age of 2000, you would say, well, probably this isn't a person who's 2000 years old. It's probably a data entry error or something, whatever. It's a statistical outlier. And so those are the uses of statistical models of databases. But you would never ask a database to answer a query using a statistical model, because it will just make up a high probability tuple. You want it to actually look in the database and see if the tuple is there or not. And that's kind of the problem we have with LLMs, I think, is that they don't have good models of their own domain of competence. They don't even seem to have very well calibrated probabilities on their own outputs, at least post RLHF fine tuning. And so, I mean, so I think we need to learn. We need to build competence models for large language models, and I think that it does. We've been able to do that for classifiers, at least in the IID setting, by doing things like recalibration and anomaly detection and so on. So that seems like it should be doable for LLMs. But I think but to get beyond the probabilistic model of a knowledge base problem, I think maybe we should actually experiment with a neurosymbolic architecture where the knowledge base is an explicit data structure, like a knowledge graph, and the LLM could be viewed as more a repository of just the linguistic knowledge, and maybe common sense, the stuff that's not going to change. We can afford to burn that into the weights of the network. But the stuff where we want to make updates, we want to tell it, who won the baseball game yesterday. We should be able to just tell it and have it update the knowledge graph and not have to modify the weights. And so we can imagine that an architecture somewhat like a retrieval augmented LLM could retrieve the relevant knowledge from the knowledge graph and then generate the answer from its linguistic knowledge. Now, there's evidently I've learned from talking to linguists that there is a long controversy about the extent to which you can separate world knowledge from linguistic knowledge. I was told that only the most diehard Chomskyan thinks that there's a clean API that separates those two concerns. But uh, but I hope we can explore that boundary and figure out, what aspects for the changeable aspects of the world we'd really like to pull those out of the LLM and represent them explicitly. And right now, retrieval augmented models suffer from this problem that they still can hallucinate or confabulate even when they're doing retrieval. Right? We haven't found the magic to restrict them to only using the retrieved documents to answer the question. So I think that's still a challenge of trying to find this boundary and figuring out how to train systems. And then, of course, the big issue is now how do we have to go back and ask, well, now how can we do that end-to-end learning? Given a new document, I need to be reading it and asking, oh, I already knew this fact because it's in my knowledge base. Oh, here's a new fact. I should add it to my knowledge base. Or is this something that I should really trust enough to add to my knowledge base? I mean, actually, a naive model of a knowledge graph is that it's like a single snapshot of everything that's true. But that's not going to work at all. We're going to need to have micro theories where, here's a set of things in the knowledge graph. This is stuff that, I don't know, anti-vaxxers believe. And here's a bunch of stuff that epidemiologists believe, and whatever. We need to have, and here's stuff that we believed was true before the year 2000, but now we don't believe is true anymore. I mean, we need to have, this has to be a much more complicated structure. And of course, people have worked on this in symbolic knowledge representation, and in databases. So I think all of these problems can be dealt with, but they need to be now to interact with the learning process. As we're reading documents, we need to understand the context and which aspects of the knowledge base the update should go in. Or maybe it needs to be, the system has to say, I'm not sure, and put it someplace where it can put probabilities on it. I don't know. And then if we want to bring inference into this, we also want to say, okay, well, maybe I don't need to add this to my knowledge base because it's a fact I could easily have inferred from stuff I already know. So, and how do you then orchestrate inference into this learning process? I think these are really tricky challenges that would need to be developed. But my vision is that you would have a system. Again, I'm very much inspired by this paper by Kyle Mahawald, Anna Ivanova et al. On dissociating language and thought in large language models, a cognitive perspective, where they look at the neuroscientific evidence for modularity in the brain and the idea that factual knowledge is separate in a separate area from linguistic knowledge, is a separate area from reasoning and planning and metacognition. And right now our LLMs, as far as we can tell, have mushed all together. Well, they're missing some of those functions, and the remaining ones are all entangled in a single network, although maybe some of this mechanistic interpretability will be able to tease those apart.
Yeah, that's really interesting. And I guess as you've kind of talked about, you have this suite of different modules that we might want to develop that go from planning to, of course, you have metacognition, formal reasoning, language understanding. As you said, it might be a little bit more difficult to disentangle from some of these other components than we might think, is one of its own. And then we have sort of common sense, factual world knowledge. And like each of these partitions is sort of a very difficult problem of its own. And one thing to what you said that seems worth thinking about and kind of, I guess, empirically investigating as we try to build systems like this is to what extent are language capacities possible to disentangle, to isolate from things like how we tend to reason about the world. I think there is at least some traditions or people in philosophy who will think about the ways that we sort of read off the idea that maybe things in the world are causally connected or reason in that way because of the structure of our language. And of course, that's going to depend maybe on which particular language you learn, for instance. And so you have a lot of sort of different kind of psycholinguistic tendencies there and things like that. But it does feel like there's maybe something to how these questions are going to be kind of empirically investigated as you go down a research path like this.
Right, and I think we mustn't overestimate the capacity of our capacity to do reasoning. Right, I think I find that my deepest reasoning is done by writing. And so I'm really using an external medium to keep track of my thoughts. My thoughts are typically represented linguistically or possibly with diagrams. And of course, this is a big point that Herbert Simon made. This is the role of external memory. He would call this, and but somehow we learn to think out loud or to think through our external memory, and language certainly is playing a big role there. So I grew up at a time when John McCarthy, of course, was a huge influence at Stanford, and his whole perspective was that the core inference engine was going to be a logical reasoning engine. And now, of course, LLMs, where people are saying, well, maybe the core engine is going to be this linguistic engine. I don't think either is sufficient by itself. I think we'll need some mix, but it is possible to. I guess we don't know what that mix should be.
Well, this is a really interesting, I think, kind of alternative to the research program that everybody seems to be throwing everything at right now. And so I'm really thankful that you're continuing to push for thinking about this sort of thing. And I think this is probably a good note to end on, too. I think for anyone listening, that really I also hope that people can be a little bit more imaginative in the types of research directions and things that they want to build than I think sort of the dominating sequence of papers seems to be right now. And so I'm really thankful to you for pushing this line of work forward and for taking the time to speak with me today. So thank you again.
Well, it's been a pleasure as always. So I hope we have a chance to talk again in the future.
And that is a wrap, my friends. As I mentioned at the start of the episode, you can subscribe to The Gradient on Substack to receive not just this podcast, but also our articles and newsletters directly to your email. You can also visit us at thegradient.pub, where you'll find all of that, as well as more information about The Gradient and how you could even contribute if you're interested. And finally, if you enjoyed this episode, we would really appreciate your feedback. If you'd like to leave a comment or review, we'd love to know how we can make this series more interesting and informative to you. And with all that, I'll leave you until the next episode.